Hey, good morning, everybody. Thank you very much for being here at the Temporal flagship meetup. We have a cool agenda for you today. Both presentations from Temporal. Tom will present and I will present. But before we do that, let me quickly introduce Vanessa. Vanessa is our new community manager at Temporal, and she's going to share a few points about replay and the meetup in your area with you.
Hi, Dominic. Thank you so much for handing over. Good afternoon, good evening, and good morning to everybody. As Dominic mentioned, my name is Vanessa Rabankwa. I am the new community manager here at Temporal, and I look forward to all your questions in Slack and all your feedback. That would be great. So next, I'd like to talk about replay. So the CFP for replay has opened for our conference in September. If you haven't already, please scan and send your talks through. And next, please, Dominic. So we have a long list of meetups coming to you in the area near you. So please scan and find out where the next meetups are. Stay engaged in the Slack channel. We actually are starting like a separate channel in Slack for us to just be able to promote our events and our conferences. So I look forward to seeing and hearing from everybody. Like I said, feel free to Slack me or DM me or send me an email. Thank you, Dominic.
Hey, thank you very much. All right. And with that, we immediately jump into the agenda. Tom is first, and Tom will give you an overview of our new course, Temporal 102. And then I will follow that with the FOSS Asia recap when we talk about failure handling. Tom, please do take it away. I stop sharing my screen and the stage is all yours.
All right, perfect. Thanks so much. All right. I'm going to share my whole desktop over there. Okay, do you see a screen that says a preview of Temporal 102? Okay, great, because I've got a few monitors here, and so I got to make sure it shows up on the right place. First of all, I want to say thank you very much, Dominic, for giving me the time. I've spent a lot of time working on Temporal 102 during the last few months, and I'm really grateful to have the opportunity to give our community a preview of what's in this course. I'm going to begin by explaining the target audience I had in mind when I designed the course, and that's software developers, specifically software developers who need to understand the fundamental concepts, tools, and techniques needed to create and run basic temporal applications in Go. People who understand how to develop and execute temporal workflows and activities, navigate the web UI, configure and run a worker, and grasp the high-level interactions between the temporal application and temporal cluster as their workflow executes. These are all things that I covered in the Temporal 101 course, so I strongly recommend taking that if you haven't already done so before you start Temporal 102. The code examples and hands-on exercises that I include in this course are written in the Go programming language, but I want to be clear about the amount of Go expertise needed. It's fairly low, although it's slightly higher than Temporal 101 due to what's covered in the course. I've tried my best to avoid unnecessary use of Go language features so that it's accessible to developers who feel more comfortable with other languages. I think that a Java developer or a TypeScript developer will be able to go through this course, follow the instructions, understand the code, and get the concepts and really get a lot out of it. But by the way, we've recently published the Temporal 101 course in TypeScript, and we're working on a Java version of 101 too. We plan to follow the same pattern here. So we've developed Temporal 102 in Go, but we're later going to make it available in other languages as well. In fact, our team is going to be teaching both Temporal 101 and 102 in Go, TypeScript, and Java as live workshops at the Replay conference this year. So there's something to look forward to if you're coming to Replay. Now I want to explain what we cover in the course. There are two ways of going about this. One way is I could just list a bunch of topics, but a more user-centric approach is to tell you what skills you'll gain by taking the course. So I'm going to start with that. There are 4 course competencies, and these are the things that are broad outcomes that result from successfully completing the course. That's being able to apply Temporal's best practices for application development, validate the correctness of your application through automated testing of your workflow and activity code, debug problems with a workflow execution by evaluating its event history, and being able to maintain and enhance your applications over time by safely incorporating changes and deploying them to production. Those 4 competencies collectively represent 27 specific learning objectives, such as learning how to configure a temporal client to access Temporal Cloud or a secure self-hosted cluster. We're learning the role of sticky task queues in workflow execution. We're understanding which types of changes you can safely deploy without versioning, and how to implement versioning in your code when it is necessary. There are 10 chapters in this course, and this includes an introduction, 8 content chapters, and a conclusion that reiterates the essential points and provides some links to additional resources where you can learn more on your own. There's also 5 hands-on exercises. Just like with Temporal 101, we provide a link to a free browser-based exercise environment with Gitpod, as well as instructions for how to set up a development environment you can use to work through the exercises if you prefer doing that locally. The course begins by covering some key concepts such as the structure of a temporal application, how it communicates with the temporal cluster, how developers can integrate temporal into other applications, and then it dives into some best practices such as how to structure input and output data, how to select appropriate workflow IDs, and how to use temporal's logging APIs. After the first hands-on exercise, it covers the use of timers, and this is followed by an exercise where you'll see firsthand that Temporal can automatically recover from work or crash, as if it had never happened at all. That foreshadows some material later in the course where you'll learn how it's able to do that. In between those points, you'll learn how to develop and run tests for your code, debug several types of workflow execution failures, and learn how to interpret the event history you see in the web UI. Following an explanation of application deployment, during which we illustrate deployments involving both self-hosted clusters and Temporal Cloud, you'll learn everything you need to know about Temporal's determinism constraint. This includes learning how history replay works, why Temporal requires determinism, what happens when your workflow includes non-deterministic code, and how to identify and correct those problems. This provides the foundation for the last content chapter, during which you'll learn how to use versioning and then implement it for yourself during the final hands-on exercise. All in all, the focus of this course is not to teach you how to use various features of the Temporal SDK. Instead, it builds on the foundation laid by Temporal 101. That is, it explains how to develop a basic temporal application. That's something covered in Temporal 101, but this course teaches you what you need to know in order to deploy it to production and maintain it over time. Many of the demonstrations and hands-on exercises that I include in this course do this by setting up scenarios where something goes wrong, so you can learn from this in a safe training environment and understand how to identify, resolve, and avoid those problems in production. Excuse me. I'm going to take a drink here. I've got a bit of a cold, and my cold medicine is making my mouth really dry. Okay, now that I've described what's in the course, let me explain when it will be available and how to get access. Tomorrow, which is April 26th, we're going to make Temporal 102 for Go available to everyone who has signed up for early access to our courses. If you go to the course page on learn.temporal.io, and I've put the URL to this specific course on the bottom of the screen, you can sign up there if you haven't already and get an email tomorrow with details on how to access the course. And by the way, this course, like Temporal 101, is completely free. You don't pay for the course, you don't pay for the exercise environment, it's all completely free. And that's a huge investment on the part of Temporal. That's something that I really appreciate, and I think demonstrates Temporal's commitment to the open source community, that we not only make the software available freely to people, but also teach them how to use it. And I'm really proud of Temporal for doing that, and I hope you all appreciate that as well. This raises the question, I say it's a beta here. This raises the question is, what does beta mean in the context of a training course? Well, I'm a curriculum developer here at Temporal, but like others on our education team, I've also spent a substantial part of my career working as a software engineer. And so the course beta is basically the same concept as a beta for a software project. The course is complete and it's been through internal review. We're still making some small improvements, but we want to get it into the hands of our users as soon as possible because we feel that they'll benefit by taking it and will benefit from their feedback. So by initially making it available to just the people who signed up for early access, we can spend more time working with them, listening to their feedback, and then making further improvements before we roll it out to the general public. That's going to happen in next month. I've just explained who this course is for, what it covers, and how you can get early access to it. Now I'd like to give you a preview of it by presenting some material from the course. One of the most important concepts to understand in Temporal is how the code you write in a workflow definition translates into interactions with a temporal cluster. This is done through the use of commands, which the worker issues to the temporal cluster based on specific API calls in your workflow code. Understanding how this works will help you to understand how Temporal itself works. So this course builds on the material that I'm going to present here, and it teaches you how these commands map to events. That's what I'm going to show here, but or rather, I'm going to show how the workflow code maps to commands. Later in the course, I explain how commands map to events. That's going to help you interpret the event history. I'm going to explain how Temporal uses history replay to recover the state of a workflow execution. That's how Temporal provides the reliability guarantee that it does. And then you're going to learn also in the course why Temporal requires determinism in your workflow code. And this will help you to understand whether a given change will break compatibility with workflow executions that are already in progress. So here's the code for a basic temporal workflow definition. It's actually pseudocode because I've simplified some aspects of the syntax in order to make it easier to follow and to better fit the limited space that I have on the screen. For example, I've removed the error handling code and I'm using a string as a return value rather than a struct, which would better reflect the recommended best practice. Although such details are important for production code, they sort of distract from the points that I want to make here. However, the course contains a complete working example of the actual code for this course. I want to give a quick overview of what this code does before explaining it in greater detail. It simulates the processing of a very simplistic pizza order. As with any workflow that executes one or more activities, it begins with a few lines that define the parameters of their execution. In this case, it sets a start to close timeout of 5 seconds. It then goes on to iterate over the pizzas that make up the order, adding up the price of each one to calculate the total cost of the order. Then it requests execution of an activity that returns the distance to the customer's location. If the customer requested delivery but is determined to be more than 25 kilometers away, it returns an error, which is going to fail the workflow because the business logic dictates that this is outside of the service area. Otherwise, it then goes on to sleep for 30 minutes, which allows time for the order to be cooked and the pizza to be delivered, and then it requests execution of an activity that will bill the customer. Again, it's a very simplistic workflow, but it's one that will illustrate the concept of commands and how they relate to temporal. So a workflow is simply a sequence of steps, and each of those is represented by one or more statements in the code. Some of those steps are internal to the workflow. That is, they do not result in any interaction with a cluster. Examples of these include things like setting parameters or performing calculations or evaluating variables or populating data structures. I'll highlight these things in white as I step through the code. In contrast, there's other steps within the workflow that do result in interaction with a temporal cluster. I'll highlight these in yellow as I step through the code. For example, requesting an execution of an activity results in the temporal cluster creating an activity task and adding it to a task queue. The workflow sleep call that I've included here is another example. It results in temporal cluster starting a timer with a duration of 30 minutes. Returning an error from a workflow function causes the temporal cluster to mark the workflow as failed. But if you return without an error, it causes temporal to mark the workflow as completed. So these are examples of things that result in interaction with a cluster. In this workflow definition, the first several statements here are internal to the workflow. That is, they don't result in any interaction with a temporal cluster. By the way, if you ever saw the determinism video that I did with Dominic that's on our YouTube channel, this is what he meant by an internal step. As the execution of this workflow continues, the worker reaches a statement that does require interaction with a temporal cluster. In this case, it's a request to execute an activity. This causes the worker to issue a command to the temporal cluster, which requests the desired result and provides the details required to achieve it. For example, the schedule activity task command contains details such as the name of the task queue, the activity type, and the input parameter values. This command is what initiates the scheduling of an activity task and the resulting execution of the code in the corresponding activity definition. I'll cover that in more detail in a moment, but I'd like to show a few more examples first. Since the workflow code is retrieving a result from the activity execution, it blocks until the activity function returns. Afterwards, the worker continues executing the workflow code. The next few lines, which I've highlighted here, evaluate a couple of variables. Depending on the outcome, it may return an error, which would cause the workflow to fail. However, let's be optimistic in this case and assume that this is a delivery for a nearby customer, so the execution will continue. It now reaches the workflow sleep call, which is another statement that involves interaction with a temporal cluster. This causes the worker to issue another command, one which requests that it starts a timer. The duration is one of the details that's specified in this command. The next few lines, highlighted here, create and populate a data structure that represents the input for the next activity. While this is related to the activity, it doesn't involve any interaction with a cluster. However, the next statement does. It requests the execution of an activity, so the worker issues another command to the temporal cluster. Again, this contains the name of the task queue, the name of the activity type, and the input parameters, the data represented there. Finally, when we return from the workflow function, this also results in a command. In this case, we're returning a result and using nil for the error. So the worker identifies this as a successful completion of the workflow execution. And in response, it issues a complete workflow execution command to the temporal cluster. And this includes the value returned from this function. So I hope these examples have helped you to recognize that calling certain APIs, which are provided by the Temporal SDK in your workflow code, will result in commands that the worker issues to the temporal cluster. Thanks again for your time and attention. Again, the beta for Temporal 102 and Go begins tomorrow, so please visit the URL that you see here and sign up to be notified when we release the course. I think we have some time for Q&A, so I'll stop sharing my screen now and answer your questions. Okay, looking at the courses here, or the questions rather, Omar Sharif asks, is it Go only? Yes, this course, right now, the initial release of this course is available in Go. But we will later make it available in TypeScript, in Java, potentially other languages in the future. I think that also addresses Ashwani's question. Is there a plan to have this in Java? And Giancarlo asks, or says, that he would love to get a TypeScript version of this course. That's coming soon. We're going to have that available later in the year. We'll be teaching that at Replay. And of course, a self-service online version of the course in TypeScript will also be available. Ezra asks a question, what's the status of the Rust SDK, not the core SDK, but the Rust worker runtimes? That's a question not about that course, so I'm going to let somebody else answer that.
I might be able to help a little bit there. So it's on our minds. It just does not have a specific date. That's the best I can offer. Sorry.
Okay. Any other questions about the Temporal 102 course or about temporal training in general? Okay. I actually, let me share one other thing. I can share my screen again briefly and point out something in the documentation. So I was explaining the concept of commands there. And so if you go to the documentation over on the left side, it says references. There's actually a commands reference there. It's the second link. And if you click it, this is a list of all the commands in Temporal. So schedule activity task, start timer, cancel timer, and so on. There's actually only 13 of them. So Temporal is actually pretty easy to understand. You could understand and remember all of these, and the commands that Temporal generates is very important to understanding the concept of determinism, and that's a key theme in this course. So this is where you can find information about those commands, and every command that gets issued to the cluster is going to result in one or more events that are logged by the cluster, and there's a handy reference of all the different events. There's a lot more events, I think maybe about 35 or 36 off the top of my head, but those are all listed there as well.
Awesome. Tom, thank you very much. If anybody still has questions, please feel free to post in the chat. And Tom, if you could stick around for a little bit and then answer the questions as they come in. I want to say Brian had a question how Temporal is different than AWS Lambda. I'm going to take up on that question. I will not forget about it, but I'll continue with the agenda first, and then after we're done with that presentation, we'll revisit that particular question, because it's always a good question. But first, let me go through my first Asia presentation. You can see the screen, right? Awesome. So I had as I already said in the very beginning, I had the fortune to present at FOSS Asia in Singapore 2 weeks ago. And the topic of FOSS Asia, the conference in general, covers everything open source related, from distributed systems, cloud computing, but also to machine learning, IoT, and robotics. And I was on the cloud track presenting my presentation, handling failures from first principles. So I would like to give you a recap of that presentation. So Werner Vogel, the CTO at AWS, famously said, everything fails all the time. No. So for Werner Vogel, it was not a question of how do we avoid failure. For Werner Vogel, it was a question of how do we handle failure. And I guess in this case, I do not need the introduction anymore, so I jump over that. And we get to the question of what Temporal is just a little bit, so answering the question that Brian asked, and that is that Temporal is an open source platform for durable executions. Yeah? And durable executions are to distributed systems what transactions are to databases, an abstraction that enables you to build applications as if failure doesn't even exist. Yeah? But to provide this guarantee to our users, Temporal built a lot of expertise in failure handling. So I was very happy to be at the FOSS Asia Summit to talk about failure handling from first principles. Now, a first principles approach breaks a domain into its basic principles and then builds an understanding from these basic principles, yeah, rather than relying on unspoken assumptions or on conventional wisdom. So in this presentation, we will think holistically about failure and failure tolerance. So a failure is an unwanted, but nevertheless possible event. And failure tolerance is a guarantee. Yeah? Failure tolerance refers to the guarantee that a system functions in a well-defined manner, even in the presence of failure. So a failure is an event in a system, and failure tolerance is a guarantee of a system. Animations don't play nice here. Okay. So in other words, If a system is failure tolerant, then the system guarantees total correctness in the absence of failure, trivially, and it guarantees at least partial correctness in the presence of failure. Now, if a system guarantees total correctness, even in the presence of failure, we speak of failure transparency. Yeah? And while failure transparency is most desirable, failure transparency is not always possible. So think of the CAP conjecture. The CAP conjecture states that a replicated data store must choose between either consistency or availability in the event of a network partition. So in the absence of a network partition, the network partition being the failure, the unwanted but nevertheless possible event, the system is able to guarantee total correctness. Yeah, that is both consistency and availability at the same time. But in the presence of a network partition, the system is able to guarantee only partial correctness, as you have to choose between consistency or availability. However, you get to choose, right? As a designer of your system, you get to choose what failure tolerance means to you. You get to choose which guarantees are important to you in the presence of failure. So failure tolerance is a design decision. Now, in order to talk about failure holistically, what kinds of failure we expect and what kinds of failure we need to tolerate, what guarantees we need to make in the presence of failure, first we have to have a look at the underlying system model. And the system model is a set of assumptions about the system. So algorithms and protocols that are correct under one system model may not be correct under another system model. Any deviation may render an algorithm or a protocol incorrect. So you can think of a system model a little like a board game. The game sets the stage and the game sets the rules, and the players have to devise a strategy to achieve the game's objectives within the constraints of the rules. And even a slight change to the rules may render a player's strategy completely ineffective. That's often a cool gimmick with extension packs, right? They change the rules and all of a sudden you got a completely new game. Now, for this presentation, we will think in terms of service orchestration. So here a system is a collection of processes. And one process is a sequence of steps. And here one step is a networked call to some upstream service. A single service call has transaction-like semantics. It's atomic. Either the call happens completely or it doesn't happen at all. This is an assumption that we're making. Basically an axiom here. However, the sequential composition of service calls does not have transaction-like semantics. The sequential composition is not atomic out of the box. But we want the sequential composition to be atomic. We want a total application, not a partial application. Therefore, in the event of a failure, we need to ensure that the process executes in one of two ways: observably equivalent to a successful total application, or observably equivalent to no application. So this slide is an extension where I tried to the FOSS Asia presentation, where I tried to capture that notion of total application or no application at all a little more formally as an LTL, linear temporal logic statement. That is, after we invoke the process, eventually each and every step shall have been executed, or a certain set of steps shall have been executed up to a certain point, and then their respective compensations need to be executed. So with this formula, we basically capture our expectation about the process execution. Now, for the rest of this presentation, we look at a more classic example, travel booking. And for Asia, that was a good example because a lot of the attendees, they traveled to be there. And so the credit cards of the attendees were charged when they booked the flights and the hotels. Each step in itself is atomic. It happens or it doesn't happen. However, every attendee obviously also has the expectation that the sequential composition is atomic. Right? We expect exactly one credit card charge and one room reservation and one ticket in case of a travel agency. And also to keep things simple, for the rest of the presentation, when we need one concrete example, we'll talk about the charge credit card service call. Now, what types of failure will we consider? In simple terms, what could go wrong? The request may be lost in the network. The service may crash before its computation takes effect. Or the service may crash after its computation takes effect. Or the response may be lost in the network. So in the absence of a response, we do not know if the intended effect has been performed or not. We cannot distinguish whether the failure occurred before the computation or after the computation. So now the system may be in an inconsistent state. And of course, additionally, the computation may simply raise an exception, right? Like an insufficient fund exception. But there is a response, and the response indicates a failure. So there is no uncertainty about it. Unless, of course, the system is lying to you, but we're excluding what's called Byzantine failures, where the system where the system model allows for components of the system to lie. We do not expect lying components. So now what should we do, right? Now it's like, well, how can we handle that failure? Failure handling always consists of two components, always. It's failure detection and failure mitigation. So the first component of failure handling is failure detection, which refers to a mechanism that detects if a failure has occurred. So personally, I struggle a little bit with the notion of failure detectors in distributed systems. So most authors, most classical papers, they focus on detecting component failures such as crashes. I prefer to cast a bit of a wider net when I think about failure detection and failure detectors. So in my perspective, a failure detector is simply a witness, a predicate that confirms that a failure has occurred. And the two most common examples of witnesses are exceptions, like the insufficient fund exception. That is a strong indicator. So basically, it's a guarantee that a failure has occurred, application level failure, and timeouts. Timeouts are a strong indicator that a failure has occurred in the absence of a response. It's a strong indicator that a failure has occurred. It's not a guarantee. So now the second component of failure handling is failure mitigation, which refers to the mechanism that resolves a suspected failure. And broadly speaking, there are two failure management techniques. One is forward recovery and one is backward recovery. So in summary, a process was a sequence of steps where a partial execution is undesirable. And therefore, in the event of a failure, we need to ensure that the process executes in one of two ways: observably equivalent to a successful total application, forward recovery, and observably equivalent to no application at all, backward recovery. So first, let's look at forward recovery. In the case of a failure, we attempt to move the process forward. Or more formally, we transition the system from its intermediary state to its final state. And as a rule of thumb, forward recovery requires repairing the underlying cause of the failure because we try to push past it. We cannot just ignore it. Now, forward recovery is a common platform level mitigation strategy in the form of retries. Right? We just gonna try again. But next, let's look at backward recovery. So in the case of a failure, here we roll the process backward, or more formally, we transition the system from its intermediary state back to its initial state. And as a rule of thumb, backward recovery does not require repairing the underlying cause of the failure, since we do not try to push past it. So backward recovery is a common application level failure mitigation strategy in the form of a compensation. Now, in order to choose the ideal failure handling strategy, are we going to use forward recovery? Are we going to use backward recovery? We also need to we need to take the failure class into account. So, of course, failure can be classified in countless different ways. But here we'll focus on two orthogonal dimensions, the spatial dimension and the temporal dimension. No pun intended, different temporal. So on the spatial dimension, we can classify failure as an application level failure or a platform level failure. And to do so, we need to think about a system in layers. Components at a higher layer make a down call to components at a lower layer, generally expecting a response. And less frequently, components at a lower layer make an up call to components at a higher layer, generally via a previously registered callback. So the end-to-end argument states that in a layered system, failure handling should be implemented in the lowest layer possible, viewed from the top down, that can correctly and completely handle failure detection and failure mitigation, because that makes a failure transparent to all layers above it. Now, a failure can be classified as either an application level failure or a platform level failure, depending on the lowest layer that is able to detect and mitigate that failure. So, for instance, an insufficient funds exception or insufficient funds failure, that indicates an application level failure. The application level is the lowest layer capable of correctly and completely resolving that failure. The failure is completely meaningless on a platform level. However, a could not connect failure message, that indicates a platform level failure. Although the application could potentially mitigate the failure, the lowest layer that is capable, that has a chance of correctly and completely mitigating that failure is a platform level. And it can do simply by retry to establish the connection. Now, on the temporal dimension, we can classify failure as transient, intermittent, and permanent, as one of my favorites. If a failure is transient, we can reasonably assume that the probability of a second failure is not elevated. Or formally, a transient failure is defined by two characteristics. First, the probability of a failure F2 occurring after a failure F1 has already occurred is the same as the probability of F2 occurring on its own. And secondly, transient failures are auto-repairing. They resolve themselves without any intervention. In our example, if the cause of the failure is a router restart, then could not connect may be a transient failure. This type of failure auto-repairs quickly, and once the router has restarted, the connection can be made. If a failure is intermittent, we can reasonably assume that the probability of a second failure is elevated. So formally, an intermittent failure is also characterized by two characteristics. First, the probability of a failure F2 occurring after another failure F1 already occurred is higher than the probability of F2 occurring on its own. But intermittent failures are also auto-repairing. They also resolve themselves without any manual intervention. And in our example, that could be that the cause of a failure could be an outdated routing table. Yeah? Then the could not connect may be classified as an intermittent failure. This type of failure auto repairs, but with some delay. Yeah? But as soon as the router updated its routing table, the connection can be made. Or we can classify a failure as permanent, where we can reasonably assume that a second failure is certain. Yeah? So a permanent failure is also defined by two characteristics. Firstly, the probability of a failure F2 occurring after another failure F1 already occurred is 100%. Yeah? And permanent failures require manual intervention to resolve. So in our example, if the case of a failure is an expired certificate, yeah, when attempting the connection and could not connect is classified as a permanent failure. This type of failure doesn't auto repair, right? It does not, the ticket does not magically become available again or valid again. Yeah? This requires manual intervention. An operator must provide a new valid certificate. And now, for our system model, yeah, and for our failure model, what could an ideal failure handling strategy actually look like? Well, let's say we do not have much information about the failure. Right? We only know that a failure occurred. Well, then, in the event of a failure, first, let's assume the failure is a transient platform level failure. So we just retry immediately. If the retry succeeds, we successfully mitigated the failure. Let's move on. Completely transparent to the application. If an immediate retry does not succeed, then we just have to elevate our understanding of the failure. Let's assume that the failure is an intermittent, but still platform level failure. So now we retry a bounded number of times, and typically with an exponential backoff to like increase our chance that the next call actually goes through. If that succeeds, we mitigated the failure. Fantastic. However, if none of the retries succeeds and we run out of our retry budget, now we upgrade our understanding of the failure once again. Yeah? Now we assume the failure is a permanent platform level failure. Now we need manual intervention. So the process itself is suspended around that failure and is waiting for a manual intervention. If the manual intervention is successful, we successfully mitigated the failure, still fully transparent to the application code. However, if manual intervention does not happen and a timeout kicks in, right, we were only able to wait 2 minutes. We were only able to wait 1 hour for the failure to resolve. It hasn't happened. No operator resolved the failure. Then at this point, we must once again upgrade our understanding of the failure and assume that it is an application level failure. Now we are ready to compensate. Right? Now we present the failure to the application. We say we have no way of pushing past that failure on time. Therefore, we need to compensate. Now, if compensation is successful, we successfully mitigated the failure. But even the compensation may not be successful. Even the compensation may fail. Then we have to escalate. We have to escalate from the cyber system to the physical system. So we basically need to escalate to a human operator. In doubt, if we cannot refund a credit card, somebody has to sit down and like write a check and mail it out. But this then happens outside of the system. So in general, yeah, failure and failure handling and guaranteeing failure tolerance, it can be like super intimidating. Yeah. But taking a principled approach will allow you to think about failure holistically and implement a failure handling strategy with confidence. And to get a head start, consider Temporal, because Temporal takes a principled approach to failure handling and implements the concepts we have discussed on a platform level, guiding you towards an ideal failure handling strategy for distributed systems. And with that, thank you very much for joining my session, in this case, joining the presentation. And then we do have a few minutes to answer any questions you may have, either for me or for Tom. And if no questions pop up, we can turn our attention to the question of what is the difference between Temporal and AWS Lambda? Did I just stop sharing? Yes, I did.
Yes.
All right. Any questions? If there are no questions, let me take up Brian's question. How is Temporal different from AWS Lambda? Now, of course, we could compare Temporal and AWS Lambda on many dimensions, but I want to hone in on what I think is the most important one. And so AWS Lambda is, as we know, function as a service. Right? But when we look at the individual function executions, they are similar to the function executions that we are generally used to. And like formally speaking, these are volatile function executions. Volatile execution means function executions with weak execution guarantees. An AWS Lambda may fail or time out. Right? So with that, AWS Lambda only guarantees you partial application. If you have a 5-step process and that particular Lambda execution fails after the 3rd step, right? There is no built-in mitigation, right? Just fails. So that is a weak execution guarantee. It is subject to failure, especially crash failure, and also timeouts. I do not remember the timeout of an AWS Lambda right now, but they do have a timeout. So you cannot push past that timeout with one function execution. Now, if you look at temporal workflows, they are durable executions. So we have volatile executions, AWS Lambda, durable executions in temporal. And the durable execution is a function execution with strong execution guarantees. It cannot fail and it cannot time out. Right? So when I say cannot fail, it cannot crash. So if you have a 5-step process, then temporal will guarantee that it executes all of these 5 steps. Even if one particular process crashes after 3 steps, temporal will resurrect and then resume the function execute without any intervention. So if you wanted strong execution guarantees on AWS Lambda, you have to build that yourself. Generally via databases, queues, and timers. Little Mac Frankenstein. Or if you need durable execution, Temporal implements durable executions on a platform level, giving you these guarantees out of the box. All right. Brian had one more question asking about the UI and if there are details about the errors so we can track them and like error levels and retries and so on. In general, yes, please do look at the UI in detail, but in general, yes, Temporal has strong observability capabilities, which is both true for the set of workflows that is currently running. So it gives you a system level view, but also for an individual workflow. So it gives you a process level point of view, or you could also argue a macro and a micro level point of view, strong observability features. Yeah. Okay, no more questions coming in. 3, 2, 1. Thank you very much, everybody. Thank you very much for joining. I am looking forward to seeing you all next month. Thank you. Have a great day. Bye-bye.